So in my proposition 10.33, the sum over I, like that's gone, all right? And so essentially I can just put like a, like an A here. And this is just literally going to be, let me skip the A actually, because once we have this, we can just multiply it by a scalar and that'll be fine. All right, so we have d dt of what I would call, let's say x1. Oh, I don't want to use that x. I'm sorry, bad x. Bad notation, bad notation. I'll try to stick with my proposition notation. I'm using y for the, so I'll say y11, right? y11 of f of t. And then you do partial y11, and then d dt of y12. And I'm just gonna say, oh, fine, of f of t partial y12 plus d dt of y21 f of t partial y21 plus d dt of y22 f of t partial y22. And of course, all of these should be taken where? Let me write this at the point. Let me give it a name. I'll call it big Q. At Q. At Q. At Q. At Q. What's Q? Q is equal to f of 1, which is actually the matrix 1, 1, 1, 1 in my current story time. I probably should have made some time other than 1, but it's too late. It's what I did. Okay, great. So then what? So let me not write too much here. What is y11? So this is literally t. This is literally t squared. This is, literally t cubed. And over here you got yourself a t to the fourth with my construction. So we're supposed to do these derivatives, and we're supposed to like evaluate at 1, right? All these derivatives are taken at time 1. Okay? So I differentiate, I get 1. So I get, partial y11 times 1 plus 2 times t, but when I plug in t equal to 1, I just get 2. Partial y12, and then I get 3 partial y21, and then I get 4 partial y22. So what to make of all this? Can I connect this to earlier things we were talking about in the course? All right. So, I mean, this is obviously the tangent vector to the path in the matrix space, where we're using, right? I mean, like my previous notation would have been something like this, right? I'd had something like gamma is a mapping from R to the 2x2 matrices, right? The gamma of t was t squared, t cubed, t to the fourth, right? And then I would have written gamma prime of 1 is 1, 2, 3, 4, right? And so, of course, that's equal to what? 1 times E11 plus 2 times E12 plus 3 times E21 plus 4 times E22. All right, so to get back and forth from this viewpoint to that viewpoint is to identify, see how this goes? Partial yij with eij. Of course, at the point Q. These are all at Q. And we are distinguishing tangent spaces at different Q's, right? I mean, that's part of what's going on here. And so I will let you read the example in the notes, which is a little bit more nuanced. It's actually, the domain is two-dimensional, right? So when the domain is two-dimensional, there's more to talk about because you're not just mapping one derivation, you're mapping two. And to understand how an arbitrary vector, see if you can understand how the basis maps, then you can understand how an arbitrary vector maps. So here the basis for the domain is just DDT, because the tangent space is one-dimensional. Yeah. And yeah. All right, so let us go on then. All right. So the next thing we're up against is the so-called cotangent space, all right? So what is the cotangent space? So cotangent space. Well, exactly. Yeah, that's exactly it. It is the dual space of the tangent space. So T star PM is equal to, alpha from TPM to the reals such that, alpha linear. So yeah, it's literally the dual space in the linear algebraic sense to the tangent space. And all right. So I don't trust my notes. All right, so I think I need to deal with the issue of there's a slightly subtle issue in here. How is the differential going to be defined? Suppose we have, so this is going to be a convention. All right, and I'm not saying the convention yet either. We're going to discover it, okay? So if we have F is a mapping from, say, the manifold to the reals, all right? And then we talk about df, right? Well, df acting on what? Acting on a derivation, right? What's it defined to be here? Well, you know the story. So if our coordinate over here is, let's say, t for one, we often use t for one-dimensional real. Then I have to define this essentially by, how it acts on a function g, right, of t. And so by definition, our previous definition, this is just our definition, right? xp of g composed with f, right? But specifically, if we look at that, we can let it act on t, right? And that will give us, xp of t composed with f, right? But this is kind of dumb. Because t is the Cartesian coordinate on R, which is just the identity map on R, which means t composed with f is just f. Right? Now, so, yeah, this is xp of f, right? That's what that is. But what does an arbitrary vector on RT look like? So it looks like what? V is equal to v of t times partial t, right? At the point t naught, let's say. So, okay, so that means that, if I calculate df of xp, it's just going to be apparently xp of f, right? And if I do this at time t naught, it's times partial, well, I use d's in this case, d dt at t naught, And so here's the custom. The custom is, in the case of one dimensions, to just drop the d dt. So a custom, drop it. So in this particular case, the usual notation is just this, d sub t naught of f at xp is equal to, just x sub, I guess, well, x sub p of f. Well, not, this is at p, I'm a dummy. That's at p. Come on. Sorry about that. Dummy. Me, not you. So, more to the point, this is a definition. dpf of x is equal to x of f for, f mapping from M to R. And x an element of the derivations at P of M, okay? Now, admittedly, if you want to be fussy, this goes counter to my push-forward definition. All right? I admit that. So if you're a sufficiently fussy person, you'll develop different notations for both and not conflate them. But this is a common identification and stuff I've read, studied, been tested on, junk like that. So check this out. What happens then when we look at dp of x upper I, right? If this acts on partial xj, right, at the point P, what do you got? Well, you've got partial xi, partial xj at the point P, right? Which is the Kronecker delta. We proved that last time, right? So what's this show you? So I don't think I emphasized it enough, but earlier today we proved that the tangent space to P at M is equal to the span of partial xi at P, right? That is a basis for the tangent space at P. Okay, so in view of this custom, this convention, if you will, and this simple calculation built off the back of what we did last time, we now can see that the differentials are in fact the dual basis to the partial derivatives. So you see TP star M is going to be the span. I haven't proved this yet, but not hard to prove given what we have in front of us, dpxi. At least this much is for sure true. This is a dual basis to that. So we expect that we can write dual vectors as linear combinations of the dual basis. Let's do that. Let's work it out. How do you think the components of a dual vector are going to be found? Well, this is exciting. See, we are really close to getting to tensors on a curved space. Like we're getting there. Because once we have the basis and the dual basis, then we can start combining them, wedging them, and all that jazz. So we're getting there. So if alpha is an element of the dual space, so I'm trying to fix the point at the moment, right? Once we get to vector fields and differential form fields, all of a sudden we'll start thinking about p varying. And that's a different story slightly, but not too different actually. But anyway, so here we believe that this can be written, well, let's try it out. So what is, well, excuse me. I should say, from the general linear algebra that we've done before, we've already proved that if it satisfies this condition, it is a basis for the dual space. So it's a basis for the dual space. The question is how to find the components for it, right? So, yeah, so let's just write alpha is equal to the sum over c lower I dx upper I. All right, the question is, what are the c sub i's? We know they exist because of our general work in the dual space of linear algebra before, but what are they? Okay, so what does this act on? This acts on derivations, right? So what would the, I mean, look, this kind of tells you right here what you want to do. You want to let alpha act on the jth coordinate partial, right? And then, and I really should have a sub p here, but I you know, at some point I stop adorning p's on everything, and you'll forgive me. I'll try to put the p's there for a moment, but you know. Anyway, that's the Kronecker delta, which gives us just back what? We just get ourselves a c sub j. So lo and behold, alpha is equal to the sum, let's say I equals 1 to n of alpha acting on partial xi at the point p times dx upper I at the point p. There you go. That is actually how we find the components of a dual vector. Yeah. Perfect. That brings us now to, oh, I guess there's one other thing I should mention. I don't think I quite wrote this yet, but notice that this is like a kind of probably a somewhat important remark, that if we have df acting on partial xi, what do we get? We get exactly partial f partial xi at the point p, right? That's how that works. Again, that begs the convention I just erased, because otherwise, if it was a genuine push forward, we'd have it would be an active object, right? It would be a derivation on R, and we're just suppressing. We're saying ddt. We're just setting ddt to 1. We're identifying the derivations on set of real functions with numbers, which is reasonable because every derivation on a set of real numbers is just a multiple of the derivative with respect to the real variable, which is kind of silly, but anyway. So next up, we will do differential forms. Woohoo! Again, my apologies for not doing more today. I'll go overtime tomorrow. I'll make up for it, okay? You're not going to be too tired tomorrow for that, are you? No? Okay, you're not like, going to get up at like 3 in the morning and like study math or something, right?
Tomorrow.
Yeah, tomorrow you're not getting up at 3 in the morning, right?
To do complex.
Do complex? That's the plan?